So, Assalamu alaikum everyone. So, previously we started the topic of the filters, but we couldn't cover it in much details. So, we have to cover the active filters as well according to our course outline. So, you can listen to this lecture during the time left for your exam. So we were studying about the filters. So we discussed that filters are actually frequency sensitive devices. It means that their output of the signal will be actually varying with the frequency of the input signal. So these are actually frequency sensitive devices, and as the name is also suggesting that they will be filtering something. So in case of our electronics, filters are actually those devices which are actually filtering some particular frequencies of the signals. So we studied that के filters को हम दो types के अंदर divide कर सकते हैं. So the first one is the passive filters, which are actually made up of the passive devices such as the resistor, inductor, and the capacitor. So these are all passive devices. While the second type of the filter is the active devices, or active devices हम इनको क्यों कहते हैं, because they are actually taking some power from outside, power supply or the power source. For example, our transistors and operational amplifiers. तो हमने पढ़ा है कि उनकी बाइसिंग के लिए जो है वो हमें एक एक्सटर्नल पावर सोर्स अप्लाई करना पड़ता है. सो दैट्स वाई we call them active devices, and these devices are actually needed when we also want some gain at the output. So, or the conditions when we don't want to lose the strength of our input signal. So for that particular application we need the active filters. फिर हमने पैसिव फिल्टर्स के डिफरेंट जो टाइप्स हैं वो हमने कुछ स्टार्ट की थी. सो वी हैव अराउंड 5 different types which are the major types of the filters. So the first one is the low pass filter, second one is the high pass filter, and then there is the band pass filter. So band pass means एक particular frequency के band को, bandwidth को, that is actually a specific range of the frequencies. So our filter will be actually letting it pass, and in the band reject it will be rejecting or stopping or filtering some specific frequencies of a limited bandwidth range. And then there is the all pass filter. So that is basically used when we have to match the impedance of our input circuit with the load. So that is actually not filtering any kind of the frequencies, but that is just changing the impedance of our circuit, just like we studied in case of the operational amplifiers, जो कि हमने buffer circuit के अंदर भी पढ़ा था. So the first type, that is the low pass filter. So low pass, you can easily remember it by remembering that low pass, that it will be allowing the low frequency signal. But it will be rejecting or stopping the high frequency signals. So जैसा कि हम जानते हैं कि the reactance of our capacitor is actually inversely proportional to the frequency. यानी जब भी हमारी frequency high होगी तो reactance of the capacitor will be low. So there is the inverse relationship. So if we have a low frequency signal अगर होगा हमारे पास from the input, so for the low frequency signal the capacitor will have a very high impedance. तो हमारे पास ये जो signal है, it will not go in that direction through the capacitor due to the high impedance, and it will just move towards the output side. So this is basically the low pass filter. So we have a resistor and a capacitor in series. So जब भी हमारे पास लो फ्रीक्वेंसी का जो सिग्नल आएगा तो वो कैपेसिटर में से पास होने की बजाय that will be passed towards the output signal. एंड ऑन द अदर हैंड जब हमारे पास एक हाई फ्रीक्वेंसी का सिग्नल आ जाएगा, so for the high frequency signal capacitor will be offering a low reactance, low impedance, and due to the low impedance that signal will be moved through the capacitor. So that's the main principle of the low pass filter कि ये low frequency signals को तो allow करता है pass होने का, but for the high frequency signals it is actually stopping them. So if we want to look at the frequency response of the low pass filter, so जब भी तो हम इसका बॉडी प्लॉट जो है वो हम ड्रॉ कर लेते हैं. तो बॉडी प्लॉट के अंदर वी नो दैट के हॉरिजेंटल एक्सिस के ऊपर हमारे पास फ्रीक्वेंसी है, एंड देन ऑन द वर्टिकल एक्सिस वी हैव द मैग्नीट्यूड और द गेन ऑफ द सिग्नल. तो हॉरिजेंटली हमारी फ्रीक्वेंसी वेरी हो रही है. सो फॉर द लो फ्रीक्वेंसी सिग्नल्स व्हाट विल बी हैपनिंग इज कि लो फ्रीक्वेंसी जब हमारे पास सिग्नल होगा फॉर द पर्टिकुलर लो फ्रीक्वेंसी सिग्नल्स there will be no change in the gain, it will be almost constant, but after reaching some specific point it will be start decreasing. So that is basically the frequency response of the low pass filter. तो अब इसके अंदर जो important point है that is a -3 dB point over here. So that is the point over here, and we say that that is the -3 dB point, और हम इस point को we denote it with the critical frequency FC, और इस critical frequency को हम corner frequency भी बोलते हैं. The other name could be the break frequency, so there are different names for this particular point. So the thing is कि after reaching this particular point our magnitude actually starts falling, and और इसकी जो slope हमने पहले पढ़ी थी वो slope क्या थी कि किस रेट के ऊपर ये fall होती है, that is the -20 dB per decade, or that is the -6 dB per octave. And if we say that कि let's suppose कि हमारा जो है वो 0 dB से स्टार्ट हुआ था और इस पॉइंट के ऊपर इसकी -3 dB इसके अंदर चेंज आ गया, एंड देन आफ्टर रीचिंग एट दैट पॉइंट, सो लेट अस कॉल दैट कि -20 dB per decade है, so that will be let's say 10 FC point, so it will be reaching at that point -20. या अगर हम अदर वर्ड्स के अंदर बोलें, सो इफ़ इट्स स्टार्टिंग विद द लेट्स सपोज कि ये 20 से स्टार्ट हुआ था, तो इसका जो कॉर्नर पॉइंट आएगा या कॉर्नर फ्रीक्वेंसी जहाँ पर इसका मैग्नीट्यूड 17 dB हो जाएगा, दैट विल बी दैट पॉइंट, और फिर वो करते करते यहाँ पर पहुँचते पहुँचते दैट विल बी द 0. सो दिस ऑल डिपेंड अपॉन द रेंज ऑफ द हॉरिजेंटल एंड द वर्टिकल एक्सिस. तो अब ये जो टर्म्स हैं हमारे पास, दैट इज़ द डेकेड एंड द ऑक्टेव. सो लेट्स सी अबाउट देम. सो डेकेड इज़ बेसिकली द change in the frequency by 10 times, and octave is actually 2 times change in the frequency. So this all depends upon the horizontal axis कि हम horizontal axis के ऊपर कौन सा scale यूज़ कर रहे हैं. So in both cases अगर हम 10 times of the frequency यूज़ कर रहे हैं then we call it the decade, and if we are using the scale of the 2 times के मतलब 2 times frequency जो है वो change हो रही है कि पहले एक particular frequency f थी, then it became the 2f, then 4f, then 8f. So that's how our scale is varying. और हम ये भी पढ़ चुके हैं कि this is all due to the log scale, और उसी के अंदर ये dB scale भी था, और ये तब हम यूज़ करते हैं when we have to deal with the values which have the small, very small values and then very large values. For those particular reasons we have to use the log scale. तो अब हम ये चेक कर लेते हैं कि ये जो स्लोप है -20 dB per decade ये कैसे आई. तो वी नो दैट कि लेट्स सपोज कि हमारा लो पास फिल्टर के केस के अंदर जैसे जैसे हम फ्रीक्वेंसी बढ़ाएंगे सो देयर विल बी द नेगेटिव इम्पैक्ट ऑन द मैग्नीट्यूड और द गेन ऑफ द सिग्नल. सो लेट्स सपोज कि अगर हम अपनी फ्रीक्वेंसी को 10 टाइम्स बढ़ाएं या पर डेकेड बाय 1 डेकेड बढ़ाएं 10 टाइम्स ऑफ द फ्रीक्वेंसी, देन हमारा जो मैग्नीट्यूड है या गेन है वो ऑलमोस्ट 10 टाइम्स से डिक्रीज़ हो जाता है. सो फॉर द 10 टाइम्स डिक्रीज इन द गेन with the 10 times increase in the frequency, so we know the formula, that is the 20 log of the gain, और गेन हमारे पास हो रहा है ऑलमोस्ट 0.1. so this is the formula for converting any value or the voltage or the current or the power of any signal into the dB, decibel scale. तो जब आप इसको सॉल्व करेंगे then log of the 0.1 is the -1, so 20 into -1 you will be getting the -20 dB. और ये हमने चेक किया था जब हमने फ्रीक्वेंसी को इंक्रीज़ किया था by 10 times 10f, so we call it the -20 dB per decade. तो सिमिलरली अगर हम दूसरा केस ले लें ऑक्टेव वाला, कि अगर हमने अपनी फ्रीक्वेंसी को जो है वो 2 टाइम्स इंक्रीज़ किया है, तो अगर 2 टाइम्स इंक्रीज़ किया है सो फॉर द लो पास, तो लेट्स से कि उसकी जो मैग्नीट्यूड है दैट बिकेम हाफ और द 0.5. so in that particular case we get the log of the 0.5 is around -0.3. तो हमारे पास जो वैल्यू आ जाती है दैट इज़ द -6 dB पर ऑक्टेव, क्योंकि हमने उसको 2 टाइम्स ऑफ द फ्रीक्वेंसी वो हमने वेरी किया था. सो दैट इज़ द हाउ वी आर अचीविंग -20 dB per decade slope or -6 dB per octave slope. So these are two different things but for the same meaning. So now let's move towards the high pass filter. So just as the name suggests, again you can just keep it remember by simply remembering that कि high pass filter है, so it will allow high frequency signals, but it will be stopping the low frequency signal. So again the same logic, the same reason, और इसका जो सर्किट ड्रॉ होता है दैट इज़ जस्ट बाय स्वैपिंग द पोजीशंस ऑफ द रजिस्टर एंड द कैपेसिटर इन द लो पास फिल्टर. सो अब हमारे पास कैपेसिटर की जगह यहाँ पर रजिस्टर आ गया है और यहाँ पर रजिस्टर की जगह कैपेसिटर आ गया है. सो जब भी हमारे पास हाई फ्रीक्वेंसी सिग्नल होगा तो अगेन इट विल बी ऑफरिंग द लो इम्पीडेंस, एंड ड्यू टू द लो इम्पीडेंस our high frequency signal will simply pass to the output. और अगर हमारे पास low frequency signal आएगा then it will be offering very high impedance and simply it will be blocking it and there will be no signal passing in case of the low frequency signal. तो अगर हम इसका अब ड्रॉ करना चाहें फ्रीक्वेंसी ग्राफ या इसका फ्रीक्वेंसी के क्रॉस बिहेवियर, सो अगेन हमारे पास बॉडी प्लॉट है और हॉरिजेंटल के अक्रॉस जो है हमारे पास फ्रीक्वेंसी वेरी कर रही है, एंड देन वी हैव द मैग्नीट्यूड इन द वर्टिकल एक्सिस. तो क्या होगा कि जब हमारे पास पार्टिकुलर लो फ्रीक्वेंसीज हैं तो हमारे पास जो इसकी गेन है दैट विल बी ऑलमोस्ट फ्लैट एंड कांस्टेंट. लेकिन जैसे ही हम एक पार्टिकुलर पॉइंट के ऊपर पहुंचेंगे देन अगेन इट्स गेन विल स्टार्ट इंक्रीजिंग एंड देन इट विल बी रीचिंग इट्स कांस्टेंट मैक्सिमम वैल्यू. सो अगेन लेट्स सपोज दैट कि हम सेम स्केल को यूज़ कर लेते हैं कि -20 dB था पहले, एंड देन आफ्टर रीचिंग दैट पार्टिकुलर पॉइंट it started increasing और फिर ये एक particular point के बाद then it again reached its maximum constant value. So let's suppose that that was 0, and then again at some particular point we have to call it by the rule, that is the negative 3 dB point, or ये negative 3 dB point, that is the critical or the corner frequency or the break frequency. ओके तो इस केस के अंदर हमारे पास जो इसका स्लोप आता है दैट इज़ द +20 dB पर डेकेड, और वी कॉल इट द +6 dB पर ऑक्टेव. अच्छा, यहाँ पे बाकी जो है वो थ्योरी सारी सेम ही है. जो कुछ और टर्म्स हैं हमारे पास, दोज आर एक्चुअली necessary for the understanding purposes. So the range of the frequencies or the band of the frequencies for which it is actually stopping them, जहाँ पे हमारे पास जो मैग्नीट्यूड है वो 0 होती है, so we call that range as the stop band. So the same is the case for the low pass filter as well. और वो वाली frequencies जिनको ये अलाउ कर रहा है दैट इज कॉल्ड द पास बैंड. ओके, तो दैट वाज अबाउट द हाई पास फिल्टर. सो दीज आर द बेसिकली पैसिव फिल्टर्स, क्योंकि इनके अंदर सिर्फ पैसिव कंपोनेंट्स यूज हो रहे हैं. सो द बेसिक्स of the passive filters will also be used in case of our active filters. So then we have to calculate the cutoff frequency or the corner frequency. So that is actually the main point that is used for the calculations for designing the different filters. क्योंकि इस point के बाद जो है वो हमारा filters का behavior that actually changes. So that's why we are more interested in finding the that particular value for the filter. So that is the corner frequency or the cutoff frequency. So the basic formula for calculating the corner frequency is 1/2 pi into RC, and there is the some derivation for it. So we will not go into the derivation, so I will upload it later, that how we can derive this formula of the corner or the cutoff frequency. So that is the formula, and then we will move towards one of the very basic example. So we have a low pass filter consisting of a resistor equal to 47 kilo ohms in series with a capacitor of 47 nanofarads that is connected across a 10 volts sinusoidal supply, and we have to calculate the output voltage at 100 hertz and 10 kilohertz. So let's start. So we have to calculate the V out. So in case of our let's suppose for the low pass filter, that is the VO, and then that is the V in. So we know that when in terms of the voltage divider, our V output is simply equal to the V in into the impedance across the output. So that is the capacitor. So the impedance of the capacitor is actually XC, and then the sum of the impedances of the resistor and the capacitor, and that one is actually when we are also dealing with the imaginary term or the complex variable. So that comes around R square plus reactance of the capacitor of the whole square root. So now we have to calculate the V out. So but we don't know the value of the XC. So for the XC we know that the formula is XC is equal to 1 divided by omega c, and omega is equal to 2 pi f into c, and we have their values. So just by simply inputting their values for the let's suppose at f is equal to 100 hertz, so 100 into c, we have that is equal to 47 nanofarad. So when you will be solving that equation, you will be getting approximately 1 divided by the 29516 into 10 raised to the power minus 9, and then again solving it, you will be getting 33,879 ohms, or you can just simply call it 33.8 kilo ohms. So that is the value of the XC. Now you can input it in the equation 1. So after inputting it in the equation 1, our V output will be equal to the V in is 10 volts, and then you will be inputting it the value of the XC, that is 33.8 kilo ohms divided by 33.8 square plus our value is 47 kilo ohms square and whole under root. So after solving it and after performing the calculations, you will be getting around 6 volts value at the output. So at 100 hertz you will be getting 6 volts. However, the input was around 10 volts. Then the second part is that we have to calculate the output voltage at 10 kilohertz. So again, first you will be calculating the reactance of the capacitor, and after inputting the values, you will be getting around 1 divided by 2 into 3.14 into 10 kilohertz, and then C value is the 47 nanofarad. So after solving it, the value of the XC comes around 339 ohms, and then when you will be inputting it into the equation number 1, your V output will be coming around 10 into 339 divided by 47 kilo ohm square plus 339 square whole under root. So that will be approximately 0.072 volts. So you can just see that as you are increasing your frequency from the 100 hertz towards the 10 kilohertz, your output voltage is almost gone and it has decreased to almost zero. So now let's find the corner frequency, ताकि हमें पता चल जाए कि भाई किस फ्रीक्वेंसी के बाद जो है ये इसकी magnitude of the voltage has started decreasing. So we know that for the corner frequency the formula is 1 divided by 2 pi RC, and we all have the values. 1 divided by 2 into 3.14, and R is 47 kilo ohms, and C is the 47 nanofarad. So after solving this one, you will be getting around 72 hertz. So the corner frequency for this particular low pass filter is the 72 hertz. So before the 72 hertz, its voltage will be approximately equal to the input voltage, but at the corner frequency, इसकी जो voltage है that will be decreased by the -3 dB, and then after that it will be decreasing at the rate of -20 dB per decade और -6 dB per octave, जैसा कि हमने ऊपर through the frequency response हमने analyze किया था. So that is the some very basic problem related to the finding the output voltages at different frequencies and also finding the corner frequencies, जिसके बाद हमारा filter जो है वो it starts working and attenuating the signal. So now the next thing that we have to cover is the phase shift. So we are also concerned about the phase shift of the signal at the output. So the formula for the phase shift is that is phase phi is equal to arc tangent of 1 divided by the 2 pi f into r into c. So let's suppose that if we are only concerned about the phase shift after the corner frequency or during the corner frequency, so let's say f is equal to 72 hertz. So when you will be solving it, then you will be getting around arc tangent of this value that comes around after solving 0.99. So this arc tangent or the tangent inverse of the 1 is approximately 45 degree. So that's why when we say that for the low pass filter, what is the change in the shift? So we say that during the low frequencies, there is no phase shift, but as soon as the corner frequency is reached, then during that time that becomes around 45 degrees. So at that point that will be, let's say, minus 45 degrees, and after reaching that particular value, that will become around 90 degree. So that's how the phase shift is actually happening in case of our low pass filter. So the same strategy can be adopted for the high pass filter. Now the next important thing is about the second order filters. तो पहले जो है we have been studying about the first order filters. So in the first order filters there is only one reactive component, but in case of our second order filters there will be two reactive components. So we know that कि जब हमारे पास फर्स्ट ऑर्डर फिल्टर थे फॉर द फर्स्ट ऑर्डर what was the condition that we were achieving. So the first thing was that we were achieving around minus 20 dB per decade. But in some applications we actually want a much faster response as compared to the minus 20 dB per decade, that के उस frequency तक पहुंचने तक 10 times of the frequency there is only the decay of the negative 20 dB. So हमारे पास जो सेकेंड ऑर्डर फिल्टर हैं उनके अंदर वो हम यूज़ करते हैं व्हेन वी वांट अ मच फास्टर रिस्पांस ऑफ द फिल्टर. सो लेट्स सपोज फॉर द लो पास how we can achieve a second order filter, that we have to simply connect two first order filters, and here we have to apply our V in, and then from here we can take the V out. So we have R1, C1, R2, C2. So in this manner we can achieve up to nth order of the filter. Okay, so we know that के एक केस में हमारे पास minus 20 dB per decade आ रहा था. So if we are using the second order, for the second order तो हमारे पास we will be getting around minus 40 dB per decade. Similarly अगर हमारे पास थर्ड ऑर्डर हम चाहते हैं, that will be again 3 into minus 20, that will be minus 60 dB per decade. So depending upon how faster response you wish for your particular filter, you can just increase its order, but that's not so simple. We will look it when we will be moving ahead. So the thing is कि हम इसका जो response है we can increase its slope of the rollover for our particular filter by increasing the order of our filter, and by the order it means के how many reactive components you are actually adding. So हम अपने single order filter को in the form of the cascading we can increase its order. So now the other thing that is about its frequency response, जो कि हमने पहले पढ़ा था कि in case of our low pass first order filter, that is actually only minus 20 dB per decade. But in case of our second order, we will be getting a much faster response over here, and that one will be minus 40 dB per decade for second order, and this one was for the first order filter. But there is another issue with increasing the order, and that is कि हमारी जो magnitude है at the corner frequency, that will be now reduced because we said that कि ये वाला जो point था जिसके बाद जो है हमारी जो magnitude है that actually starts decreasing, that was a minus 3 dB point, and that was a critical frequency. But in case of our second order filter, that now will be a minus 6 dB. So when the magnitude has almost decreased over there, so that will be now the corner frequency, but for the second order. So what happens is there are two things कि एक तो इसकी magnitude जो है वो ज़्यादा decrease हो जाएगी at the corner frequency. So magnitude decreases with the higher order, and the second thing कि इसका जो पास बैंड है उसकी रेंज भी हमारे पास चेंज हो जाती है. So the pass band range also changes or decreases in case of the low pass with the higher order. So let's suppose कि अगर पहले हमारे पास इसका जो पास बैंड था that was something like that in case of our first order pass band, but now it has reduced by some amount. So that is the pass band for the second order. Okay, so there is actually a kind of trade-off while designing these filters that we have to take care about their pass band as well as their stop band and the magnitude of our output signal or the gain of our output signal while we are moving towards the higher order. So the last thing about it is okay, how to calculate the corner frequency for the second order filter, so that is simply 1 divided by 2 pi into under root r1 c1 r2 and c2. So again we will not look into the derivation of this formula. So for designing purposes you can just simply use this formula, and we will upload a separate document for the derivation of these formulas. So that was all for this lecture, and now we will be moving towards the active filters. Thank you.